Hello and welcome back to the channel. Today we're diving into one of the most fundamental concepts in discrete mathematics and computer science, functions and order relations. Let's start with the basic definition. A function is essentially a rule, a very specific kind of rule that assigns exactly one output to each input from a given set. Think of it like a vending machine. You put in your money and selection code. That's your input, and you get exactly one item out. That's your output. You can't get 2 candy bars for one selection, and you can't get nothing if you make a valid selection. Now, let's formalize this concept. If we have 2 sets A and B, a function f from A to B is written as shown. This notation tells us that f takes elements from set A and maps them to elements in set B. The crucial requirement is that each element A in set A maps to exactly one element B in set B. Let me introduce 3 essential terms that you'll use constantly. Domain. This is the set of all possible inputs. Think of it as all the valid coins and selection codes for our vending machine. Codomain. This is the set that all outputs must belong to. It's like all the possible items that could theoretically be in our vending machine. Range. This is the subset of the codomain that contains only the actual values our function produces. If our vending machine only has chips and sodas, but no candy, then candy isn't in the range even though it might be in the codomain. Let's work through a concrete example. Suppose A equals 1, 2, 3, O and B equals x, y, z. One possible function f could be defined as the set of ordered pairs f equals 1, x, 2, y, 3, z. This means input 1 maps to output x, input 2 maps to output y, input 3 maps to output z. Notice that each input has exactly one output. This is valid. Now, what would not be a function? If we had something like 1, x, 1, y, 2, z. This wouldn't be a function because input 1 maps to both x and y. That violates our exactly one output rule. Now comes types of functions. Let's start with injective functions, also called one-to-one functions. An injective function has a very special property: no 2 different inputs ever produce the same output. The formal definition states, a function f is injective if f, a 1, equals f, a 2, implies a 1 equals a 2. In other words, if 2 outputs are equal, then their corresponding inputs must also be equal. Think of this like a fingerprint system. Each person has a unique fingerprint. No 2 people share the same fingerprint pattern. If f maps people to their fingerprints, this would be an injective function because different people always have different fingerprints. Next, we have surjective functions, also called onto functions. A surjective function ensures that every element in the codomain is actually used. It's hit by at least one input. Formally, a function f A to B is surjective if for every B in B, there exists at least one A in A such that f A equals B. Imagine you assigning students to dormitory rooms. If your assignment function is surjective, it means every room gets at least one student. No rooms are left empty. Some rooms might have multiple students. Remember, this is about surjectivity, not injectivity, but no rooms are unused. Now comes the gold standard, bijective functions. A function is bijective if it's both injective and surjective. This creates a perfect one-to-one correspondence between the domain and codomain. Bijective functions are incredibly important because they are invertible. Think of it like a perfect pairing dance where every person from group A dances with exactly one person from group B, and every person from group B dances with exactly one person from group A. You can reverse the pairing perfectly. A classic example is f(x) equals 2x from the set of integers to the set of even integers. Every integer maps to a unique even integer, injective, and every even integer is the image of exactly one integer, surjective. Let me briefly introduce 3 other important types. Identity function. This is defined as f(x) equals x. It simply returns whatever you input. It might seem trivial, But it's like the number 1 in multiplication, it's the neutral element for function composition. Constant function, every input maps to the same output. If f(x) equals 5 for all x, then no matter what you input, you always get 5 out. These functions are surjective only if the codomain contains just that one constant value. Permutation function. This is a bijective function from a set to itself. Think of it as a way to rearrange the elements of a set. Card shuffling is essentially applying a permutation function to the deck. Let me explain function composition with a real-world analogy. Suppose you have two functions. F takes a person's name and returns their student ID, and G takes a student ID and returns their GPA. The composition G composed with F takes a person's name and directly returns their GPA. The order matters. G composed with F is different from F composed with G. It's like putting on socks and then shoes versus putting on shoes and then socks. The order of operations changes the result entirely. Inverse functions. Finally, let's discuss inverse functions. If a function f is bijective, then it has an inverse function f inverse. The inverse function undoes what the original function does. The key property is f inverse f(x) equals x for all x in the domain of f, and f inverse y equals y for all y in the range of f. Think of f as encrypt a message and f inverse as decrypt a message. Only bijective functions have this perfect reversibility property. We now transition from the theoretical foundations of functions to one of their most practical applications in computer science, analyzing how functions grow. Imagine you've written two algorithms to sort a list of numbers. Algorithm A takes n squared steps for n items, while algorithm B takes n log n steps. For 10 items, the difference is minimal, 100 steps versus about 33 steps. But for 1 million items, algorithm A needs 1 trillion steps, while algorithm B needs only about 20 million steps. That's the difference between running instantly and running for hours. This is why we study asymptotic behavior, how functions behave as their input approaches infinity. Let's start with big O notation, written as O, G, N. This gives us the upper bound of a function's growth rate, essentially the worst-case scenario. The formal definition. We say f of n equals big O of g of n if there exist positive constants c and n naught such that for all n greater than or equal to n naught, we have f of n is less than or equal to c times g of n. What does this mean in plain English? It means that beyond some point n, our function f, n, will never grow faster than some constant multiple of g, n. Think of g, n, as a speed limit, and c as a tolerance factor. Let's work through an example. Consider f of n equals 3n squared plus 2n plus 7. Is this big O of n squared? For large values of n, the n squared term dominates. The 2n becomes negligible compared to 3n squared, and the constant 7 becomes even more negligible. We can choose c equals 4 and n naught equals 5, and verify that 3n squared plus 2n plus 7 is less than or equal to 4n squared for all n greater than or equal to 5. The key insight, big O focuses on the fastest growing term and ignores constants and lower order terms. Omega notation, written as omega of g of n, gives us the lower bound, the best case growth rate. We say f of n equals omega of g of n if there exist positive constants c and n naught such that for all n greater than or equal to n naught, we have f of n is greater than or equal to c times g of n. This tells us that our function grows at least as fast as g of n. Using our previous example, f of n equals 3n squared plus 2n plus 7 is also omega of n squared because the n squared term ensures it grows at least as fast as n squared. Theta notation, written as theta of g of n, gives us a tight bound. It's both an upper and lower bound. We say f of n equals theta of g of n if f of n equals big O of g of n and f of n equals omega of g of n. This means f of n grows at exactly the same rate as g of n, up to constant factors. For our example f of n equals 3n squared plus 2n plus 7, We can say f of n equals theta of n squared because it's both big O of n squared and omega of n squared. Let me walk you through the common growth rates from slowest to fastest. Constant, O, 1. These functions don't grow at all. Logarithmic, O, log n. These grow very slowly. Binary search is a classic example. Even if you have a billion items, log 1 billion is only about 30. Linear, O, n. These grow proportionally to input size. If you double the input, you double the time. Log linear, O, n log n. This is common in efficient sorting algorithms like merge sort and heap sort. Quadratic, O, n squared. These involve nested loops over the input. Bubble sort, selection sort, and naive matrix multiplication are examples. Cubic, O, n cubed. Even worse, often involving triple nested loops. Exponential, O, 2n. These grow extremely fast. Many brute force solutions to optimization problems are exponential. Factorial, O, n factorial. The worst common case. Finding all permutations of n items requires n operations. For just 20 items, that's over 2 quintillion operations. Understanding these growth rates helps you make crucial decisions. Algorithm design. Choose algorithms with better asymptotic complexity. Sometimes a more complex algorithm with better growth rate is worth implementing. Software optimization. Focus optimization efforts on operations with the worst asymptotic behavior first. System architecture. Design systems that can handle the expected growth in data size. Performance prediction. Estimate how your system will perform as it scales. You encounter order relations constantly in daily life: heights of people, ages, grades on assignments, priority levels, and task management. In computer science, order relations are essential for sorting algorithms, database indexing, priority queues, and much more. An order relation is a binary relation that defines a systematic way to compare elements in a set. It tells us which elements come before or after others according to some criterion. Before we define order relations precisely, we need 3 crucial properties that relations can have. Let R be a relation on set A. Reflexive property. Every element is related to itself. Formally, for all are in A, the ordered pair A is in R. Think about the less than or equal to relation on numbers. Every number is indeed less than or equal to itself. Antisymmetric property. If A is related to B and B is related to A, then A and B must be the same element. Formally, if the ordered pair B is in R and the ordered pair B, A is in R, then A equals B. Consider the divides relation on positive integers. If A divides B and B divides A, then A must equal B. Transitive property. If A is related to B and B is related to C, then A must be related to C. Formally, if the ordered pair A, B is in R and the ordered pair B, C is in R, then the ordered pair A, C is in R. This is like saying, if Alice is taller than Bob, and Bob is taller than Charlie, then Alice must be taller than Charlie. A partial order is a relation that satisfies all 3 properties: reflexive, antisymmetric, and transitive. We call a set equipped with a partial order a partially ordered set or poset. The word partial is key here. It means that not every pair of elements needs to be comparable. In a family tree, for instance, you can compare ancestors and descendants. Grandmother comes before granddaughter, but siblings aren't necessarily comparable to each other in terms of the ancestral ordering. Let's examine a concrete example. Consider the set A equals the set containing 1, 2, 3, 6 with the relation divides symbolized as a vertical line. We say A divides B if A divides B evenly. Reflexive, every number divides itself. Antisymmetric and transitive. So this is indeed a partial order. Notice that 2 and 3 are not comparable. Neither divides the other. A total order takes partial order one step further by adding the comparability property. For any 2 distinct elements A and B, either A is less than or equal to B, or B is less than or equal to A, or both if they are equal. The standard less than or equal to relation on real numbers is a perfect example of total order. Given any two real numbers, you can always determine which is smaller, larger, or if they are equal. Total orders are what we typically think of when we hear ordering, like alphabetical order, numerical order, or chronological order. Hussey diagrams provide an elegant way to visualize posits. They simplify the representation by omitting self-loops. Reflexivity is assumed. Omitting edges implied by transitivity. Drawing edges upward to indicate the ordering direction. For our divisibility example with the set containing 1, 2, 3, 6. 1 is at the bottom, divides everything. 2 and 3 are in the middle level, divide 6 but not each other. 6 is at the top, divisible by everything. We draw lines from 1 up to 2 and 3, then from both 2 and 3 up to 6. This immediately shows the structure without cluttering the diagram with obvious relationships. Understanding different types of elements in posits is crucial for applications. Maximal and minimal elements. A maximal element has nothing greater than it in the posit, while a minimal element has nothing smaller. Note that there can be multiple maximal or minimal elements in a posit. Greatest and least elements. These are unique when they exist. A greatest element is greater than or equal to every other element. A least element is less than or equal to every other element. Upper and lower bounds. For a subset S of a posit, an upper bound is any element that's greater than or equal to all elements in S. A lower bound is any element that's less than or equal to all elements in S. Least upper bound, also called LUB, and greatest lower bound, also called GLB. The LUB, also called the join and denoted a join B, is the smallest element that's still an upper bound. The GLB, also called the meet and denoted a meet B, is the largest element that's still a lower bound. Let's revisit our divisibility example. For elements 2 and 3. Their upper bounds are elements divisible by both, just 6. Their lower bounds are elements that divide both, just 1. LUB of 2 and 3 equals 6, which is their least common multiple. GLB of 2 and 3 equals 1, which is their greatest common divisor. This brings us to lattices, special posits where every pair of elements has both a join, which is the LUB, and meet, which is the GLB. Lattices are incredibly important in computer science, appearing in compiler design, database theory, and abstract algebra. Our divisibility posit containing the set 1, 2, 3, 6 is actually a lattice because every pair has a join, which is the LCM. Every pair has a meet, which is the GCD. Bounded lattices have both a least element called 0 or bottom, denoted by the bottom symbol, and a greatest element called 1 or top, denoted by the top symbol. Distributive lattices satisfy the distributive property A meet the quantity B join C equals the quantity A meet B join the quantity A meet C, and its dual. These behave similarly to arithmetic multiplication and addition. Complemented lattices are bounded lattices where every element has a complement, an element that when joined gives the top element and when met gives the bottom element. Compiler design. Dependency analysis uses posits to determine the order in which operations can be executed safely. Database theory. Join operations and indexing structures rely heavily on lattice theory. Artificial intelligence. Knowledge representation systems use concept lattices to organize hierarchical information. Security systems. Access control models often use lattices to represent security levels and information flow policies. Boolean logic. Boolean algebra is fundamentally a complemented distributive lattice, forming the foundation of digital circuit design. This concludes our exploration of functions, order relations, and lattices. These structures appear throughout computer science, so mastering them now will benefit you in algorithms, databases, compilers, and many other advanced topics. That's a wrap. Thank you for watching this video. Don't forget to give it a like, share with your friends and subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.